Okay, so this is lecture 13, where we're finally going to tell you what a function is. You've been using functions for years, and I'm sure nobody's ever told you what a function is. So we're going to look at that question. There are a few spare handouts left at the front if you haven't got any. So let's remind you what you already have been doing with functions. And actually, I'm not going to start writing down hundreds of different functions because you've done so many already in A level and in calculus and maybe in ACF and so on. So C, G11 Cal, G11 ACF, and A level, etc. Okay, so just things to bear in mind are there's lots of very useful standard functions, and if you can sketch them convincingly, I'll normally let you assume from the standard sketch the standard properties of these functions, as long as your sketch is convincing. So you can use constant functions, polynomial functions, trig functions, sine, cos, tan, and so on. Where they're defined, exp and log. Log is only defined at some places, exp is defined at all real numbers. So as long as you know where your functions are actually defined and you can draw convincing sketches of the graphs, I'll usually let you say things like, we know what the graph of this standard function looks like, and from that we can see that it's clearly got these properties. That is, once we decided what properties we're looking for. So we're not going to reinvent the wheel completely. I'm going to assume that you do know some standard facts about standard functions. That was mostly about functions of one variable. Here's some functions of two variables. A function of x, y, and z, where x, y, and z are real numbers. It's just I wrote a random thing down here. X squared cos of y squared, x squared cos of yz plus e to the power of 2xy plus z, just any old function. You can combine functions in standard ways and get other functions. So I'm not going to tell you much new about that. Let me note one thing, though. You can think of this as a function of three different variables, x, y, and z, where the variables are real numbers. Or you can think of it as a function of one variable, if I put an extra pair of brackets in. Now, why do I say it's a function of one variable? This time there's one variable, but the variable is in r cubed. Okay? Now, nobody ever cares whether you put the extra pair of brackets in or not, and nobody ever distinguishes. In theory, you should perhaps distinguish between a function of three different variables, each of which is in R, and a function of one variable where that one variable is in R cubed. I mean, I'm really going to be talking about functions of one variable in FPM, so this first version is probably more accurate for the kind of descriptions we're going to be using. But people often do think of it as a function with several variables, and you can think about what the difference might be. But anyway, one way or the other, I'm not going to worry about an extra pair of brackets, and nobody ever does. Having said all that, there is a problem. What is a function? And it's just as bad as what is a relation. And maybe not quite as bad as what is a set. That is, if you assume you know what a set is, then you've got a good chance of deciding what a function is. So I will give you a formal definition later, but as usual, the formal definition is not normally very helpful. The formal definition is not really something we're going to work with very much, maybe a tiny bit, but it is useful to have it there because how do you know that it makes sense to even talk about functions if you don't really know what they are? So here's the informal definition of a function. This is the one you'll have been working with for years. Pretty much. Okay. So you're going to have a function f going from some set A to another set B. And the informal notion is that somehow it's a rule that you specify or choose that will tell you what you have to do to get from the element in A to the function value, which is going to be in B. So you take an A in A, and then whichever A in A, you're going to apply the function to it. And if it's a genuine function, you should be able to figure out exactly which element you go to in B. You don't want to have something like plus or minus square root, where you haven't made your mind up. You're supposed to choose exactly one element in the other set that you're going to go to. And all functions in this module will have that property, that from your starting point, you go to exactly one point of the other set. That's nothing special about a function. Every function will do that. Okay, so then we've got terminology. The first set, the one you're coming from, is called the domain of the function. And the set you're going to is called the codomain of the function. Okay, there'll be some warnings about that in a minute, but domain is where your function is defined, and the codomain is where you're going to. And then there's this maps to symbol here. You may not be able to see it very clearly, but there's a very slight difference in that arrow. It's got a little vertical line at the beginning. So let's maybe make that a little bit bigger. So that fig there looks like this. It's got an extra vertical line at the beginning, and this is pronounced maps to. It's the maps to symbol that tells you where x is going to go. In this case, it says, if you start at x, you're going to end up at f of x. And sometimes we'll use that in order to say what the rule is. But this only really makes sense if you've decided what your domain and codomain are, and the rule works. And you can say x is the argument of the function, and f of x is the value taken by the function. So you have function values, so this is slightly informal because what's a function? It's given by a rule. What's a rule? Well, perhaps it comes from a function. We'll try and do a bit better than that later, but you've been working with functions for years, so you pretty much got a good idea of what these rules are likely to be. It's like going to be something like x squared. You've got to square your things, or you're going to square root them but specify that it's a non-negative square root or something like that. So you know how to do that sort of thing. Here are some warnings, hopefully. Okay, so first of all, this is the maps to symbol again. X maps to 1 over x is a perfectly good rule as long as you're not divided by 0. Okay? So it doesn't define a function from R to R. This doesn't count as a function from R to R using this rule, or at least it's not enough, because it's not defined at 0. You'd have to define it separately. If you wanted to use this to make a function, you could only use this when x was not 0, and then you'd have to say separately what you wanted 0 to do. So that doesn't give you a function from R to R. And same problems go, x goes to ln x, x goes to square root x, x goes to tan x. They don't define functions from R to R, though they work on various domains, each one. So you could use that rule on some other domain, but the domain can't be R, because if you want, your function has to be defined at all points of the domain. That's the first thing you have to be able to do. Of course, not only must it be defined at all points of the domain, the value that it takes has got to be in the codomain. So even if you did allow some sort of value infinity, since infinity is not in R, you couldn't do that either, because the values taken by the function have got to be in the codomain. So it still wouldn't define a function from R to R, even if you did say that the value at naught was going to be infinity. Unless you throw infinity in and make a bigger set, you're not going to be able to do that. You can do that sort of thing starting in fourth year. You start to be able to work with infinity. And you can do things like 1 over infinity and 1 over naught if you're very careful. But you shouldn't do that before fourth year, I don't think. Right, there. OK, so if you do want to use square root of x, and that's going to be the non-negative square root. So that root x here, we use that to mean non-negative square root. That's a non-negative square root. But we're not going to allow, as I said before, we're not going to allow plus or minus square root of x. You've got to, you have to have, you're supposed to choose one point in the codomain that you're going to, not two. So you can't use plus or minus square root x. Now here's another warning about the word range. And depending on who you are, some people use range to mean codomain. That's what they do in Cambridge. Some people use range to mean the image of the function, the values taken by the function, which might not be all of the codomain. And in Nottingham, range is normally used for the, this is in Nottingham, the codomain, so here, for example, we look at 1 plus root x, that's a non-negative square root, going from naught infinity to r, then you get all the values from 1 onwards, as in the image. So the what I call the image of the function, and what some people in Nottingham call the range of the function, is actually the interval going from 1 up to infinity inclusive. So this is what we'll call this the image of the function. And we'll come back to that in a bit. So that means if you're reading a book, if you're reading a textbook and you come across the term range, you have to figure out which version of range they're talking about. And that means going back and checking, or either figuring it out from the way they use it, or going back earlier in the book and figuring out what they say the range is, because you've got a 50-50 chance, right? That's why I stick to using codomain and image, because nobody disagrees about those, at least I don't think they do. With range, there is disagreement. So you can decide your rule, and you might have the same rule, but you might decide to change your domain, or use the same domain and change the codomain. And in this module, all of those will change the function, though the last one is the least obvious of those. Okay, so if you change the rule, it's pretty obvious you've changed the function. If you change the domain, it's reasonable to say, well, at least we're working in a different place, so okay, it's somehow a bit of a different function. But suppose you keep the same rule and the same domain. So it's a function defined on the real numbers, and it's x squared. Surely that's just one function. But actually, in this module, that could still be more than one different function, depending on which codomain you choose, depending on whether you say it's going to the whole of the real numbers or to the non-negative real numbers, for example. So you could define 3 different functions, for example. So if one defined from R to R, here's the obvious one, with f1 of x equals x squared. That's a perfectly good function. You could also define f2 from the non-negative reals, still going to R, by f2 of x equals x squared. And that's a different function because we changed the domain. And that means, obviously, we're looking at a different stretch of the real line to be working on. So somehow, perhaps the properties of this function are slightly different. And they are, as we'll see. F3, we can go from R because squares are non-negative, we can use the same rule to go from R to the non-negative reals. f3 of x equals x squared. And that one looks pretty much the same as the first one. It's defined on the real numbers. You're squaring. You end up at the same place. But there is a subtle difference, which we'll see, is that, let's just get another dot there. With this one, regarding the function from R to R, we take the function x squared, there are a lot of values in the codomain that you don't hit. All the negative numbers in the codomain that you can't get at. Whereas in this last one, when you're saying it's a function from R to the non-negative reals, there's nothing in the codomain that you can't get to. So there's a subtle difference between f1 and f3 in the nature of, are there any values that you miss in the codomain? And that's going to be important later when we talk about surjective functions. Right, so rule, domain, codomain will specify your function, which is still slightly informal. So to help us understand how we might formalize this a bit, and also see what some of the properties functions might have, we're going to look at the graphs of functions. Now, I'm going to start by drawing, or attempting to draw, some standard sketches of functions for you, just to remind you what you think graphs of functions look like, before we come up with a formal definition of graph, which will be much more general. Okay, so I'll just sketch these standard functions, which I will try to anyway. Always difficult on a tablet to get it properly symmetric. So you can do better than me on this one, but I will have a go at doing y equals x squared. Oh, not too bad. Okay, there's y equals x squared. Let's have a look at y equals x cubed. But what about y equals x cubed minus x? You may not have done that one recently. That was a slightly more interesting function. You can figure out where it crosses the axis and so on. It comes up, it crosses the axis a bit, goes through the origin, goes off. It's an odd function. And this is y equals x cubed minus x, which is quite fun. And we'll come back and revisit these functions later. And notice, I said it was going from R to R, but of course, you could use the same rule with different domains, different codomains, and get various different functions out of these rules. But these things are nice polynomial functions, which means they live naturally on the whole of real line, but you could use them on some interval instead, or any set really, that's a subset of the real line, and use them to define a function. So what is the graph of a function? Well, notice what we've drawn here is with y equals f of x, the graph is really the set x f of x, where in this case x is in R. It's a set of ordered pairs. The ordered pairs that are included on these lines, right? So we look at what's on these lines. It's the point x, y, where y equals f of x. So that's also equal to x, y, where x and y are in R,
and y equals f of x. And that's a subset of r squared. So these red curves here are really my sketches of certain subsets of r squared. Now, we started with r, we defined a function on r, and we ended up with a subset of r squared. And that set of points is what the graph is, really. That's what we sketched. And that's the one that we use to explain what the graph of a general function is. Okay. So that means we've got to go back and remind you what a Cartesian product is. You take any pair of sets, A and B, then A cross B, the Cartesian product, is just a set of all ordered pairs where the first coordinate x has to be in the first set and the second coordinate has to be in the second set, of which r cross r is a special case. R cross R is a special case, x, y, where x is in R and y is in R. That's when A and B are both R. So this R is the first set and this R is the second set, but they're both R, so it didn't make any difference. But generally, if you're a function going from A to B, A is going to be the first set and B is going to be the second set, and we'll be working within a Cartesian product. And then you can form the graph of the function. So you've got a function going from A to B. A moment ago, we were going from R to R. And the graph, I said, was a set of pairs, and the set of pairs we had were basically this. Order pairs where the first element was the argument of the function, and the second element is the value of the function. And that's what's going on here. That's the same as, with those A, B, where A is in A, B is in B, and B equals f of A. You can use x and y if you like. They're dummy variables. So I could also write that actually another way. It's the same as those A, B in A cross B, such that B equals f of A. It means you get some, but usually not all, in fact hardly ever all, of the elements of A cross B. Because the second coordinate must be equal to the function evaluated at the first coordinate. And that's unlikely to be the whole of A cross B, unless, of course, B's only got one point in and the function is constant. Or possibly there might be an empty function. Let's not worry about that. Strangely enough, I haven't been able to find a standard notation for the graph of a function in the literature. Everybody says the graph of the function. So I thought graph of f would be an easy way to write graph of the function. I think some people use a capital gamma, but there doesn't seem to be anything standard that I can find in the literature. Okay, so when A and B are R, like we had before, then we're talking R cross R, and this notion of graph fits with what we had before. It's a set of points when you sketch the curve y equals f of x. As I said, it doesn't matter whether you use A and B or x and y, they're dummy variables. So this is also equal to xy in A cross B, such that y equals f of x. So it's a set of points available where the second coordinate is what you get by evaluating the function at the first coordinate. And that's the graph of your function. And with the functions, all the standard functions given in calculus, that's what you expect to see. If it's a function from R to R, then you get a subset of R squared. If it's a function from R cubed to R cubed, the graph is a subset of R to the sixth. You know, very easy to define a function from R cubed, taking values in R cubed. It could be take your vector and double it. That's a perfectly easy function. from r cubed to r cubed, the graph of that function will be in r cubed cross r cubed, which is basically r to the sixth. So the graph is therefore living in a rather peculiar space, and yet the function is dead easy, just double your vector. And then you can get more abstract than that. So in the full abstraction, graphs can be a bit peculiar, but generally they fit with what you expect. Now, what happened there? I think what's happened is my computer decided to restart. I hope not, but it's possible. I saw a warning a moment ago, and I failed to act on it. Let's see. Oh, there you go. Yes, sorry, my computer's decided to log off, probably installing itself updates, so there could be a slight delay. So I'll pause the recording while we sort that out. Okay, let's see what people went for. Possibly. Well, while that's thinking about it, I'll just tell you that you're mostly split between A and B. Oh, here we go, it's coming, I think. Mostly split between A and B, and C, quite a good minority. You're really not sure about this one, okay? And a scattering of other answers as well. So, just for those watching, I'll just point out what the answers were. It was A was none, B was 12, C was 64, D was 81, and the correct answer is 64, which is C. Okay? Now, in fact, as a rather suggestive notation, it's rather unfortunate. The set of functions from A to B is usually denoted by B to the A. Now, that's very unfortunate, but it can't really be helped. So the functions go from A to B, and the notation is B to the A, and that's the set of functions from A to B, from the set of functions from A to B. It works out quite well, though, if you're trying to figure out how many there are, because if the sets are both finite, then what you have to do is raise the number of elements in B to the power of the number of elements in A. So we write mod B equals number of elements in B, mod A, which is 4 here, mod A equals number elements in A equals 3. And the number of functions, that's the number of functions from A to B, which is the number of elements in B to the A, is, as it turns out, equal to mod B to the mod A, equals 4 to the 3, which is 64, which is all very well, but I haven't really explained why. So I'll just say something about why that is. Well, you have to decide where 1 goes, and 1 can go to any of the 4 things in B. And then you have to decide where 4 goes, and 4 could go to any of the things in B, and it doesn't have to be different from the one that 1 went to. And 6 has to go to somewhere in B, And so you have to specify where does 1 go. You have to specify where does 4 go. And you have to specify where does 6 go. And you've got 4 choices for each of these. And once you've decided where each of them goes, that's your function. Okay? So your function is determined by where the elements in the domain go. But you've got 4 choices for each, and they're independent, so you have to do 4 times 4 times 4. And you could list all 64 possible functions. It's not very exciting. You could go through systematically and say there's a function where 1, 4, and 6 all get taken to 2. There's a constant function 2. There's a constant function 5. There's a constant function 9. A constant function 13. And then there are various other functions where they get sent to various different places, with or without repeats. But the total is 64 possible. Okay, that's how that one works. So now you've got sets A and B, and you've got a function. The graph has the following property. That for every A, there's always a unique B in B with AB in the graph. You can think of that as talking about how many times does a vertical line cross the graph. I'm just going to nip back to one of the graphs of an earlier function. If you look at a vertical line, it doesn't matter which vertical line you look at, as long as you stay in the domain. It doesn't matter how weird the function is. Each vertical line, the vertical lines meet the graph exactly once. It doesn't matter. As long as you stay in the domain, okay, and you draw your vertical line, then it's bound to hit the function, the graph exactly once, because you're plotting y equals f of x, and we're only allowed one value, f of x, for a given x. There's nothing special about functions with this property, okay? So if we come back to what I just said, for every a in the domain, A is the domain. For every A in the domain, there's always a unique B in the codomain such that the relevant ordered pairs in the graph. Symbols, useful to have a notation for that. Get you used to this. For all, and there exists. For all A in A, it's true that there exists a unique B in B. That exclamation mark in there means that not only that it's telling you more than just there exists a B, but it tells you there's exactly one. So exists factorial B means there exists a unique B. Which means exactly one. Not none, not two, not more than two, but there's exactly one. Okay. And this statement about functions is true for all functions. And the warning is that in the January 2013 exam and in the January 2014 exam, it was still true that many students claimed that this is something special about a function and that only some functions have this property. But no, this is almost part of the definition of a function, that functions do this. We're not allowing multi-valued functions, okay? We're not allowing functions that don't take any values, and we're not allowing functions that take 2 or more values. Our functions take exactly one value for each point in the domain. So this is not special. Okay, I don't know whether it'll help that I mentioned that people got it wrong in 2013 and then got it wrong again in 2014, But just in case it comes up in January 2015, I would really appreciate it if you didn't say that this was something special about functions. Okay? But I wish you good luck if that turns up. Now, what happens, I can see that our computer problem has meant that we're not going to have the time that I wanted to spend on the next problem, so I'm just going to explain it to you instead. So suppose somebody gives you the graph of a function, or they claim it's a graph of a function, but they didn't tell you what the rule was, they didn't tell you what the domain was, and they didn't tell you what the codomain was. And you want to work out whether they could be telling the truth or not. So they've given you a set. They say, here's a set. I got this set by making it, by using, it was a graph of some function I chose. I'm not going to give you any more information than that. You tell me whether I'm telling the truth or not. Now, so I don't have time to get you to do this, unfortunately, so I'm going to explain it, okay? Here are 4 sets, each of which might or might not be the graph of a function. Now, how do you recognize the graph of a function when you don't know the domain or the codomain? Well, what you need to know, the domain, if it is the graph of a function, the domain can be found by looking at the first coordinates. So if S1 is the graph of a function, then the domain must consist of 0, 3, 1, and 2. You look at S2, the domain would have to be the set which has got 0, 1, 0 again, but that's okay. You could do that with care. So this second one looks like the domain should have 0, 1, and 2 in it, but we'll see there's a problem. The third one, the domain should have 1, 2, 3, and 4 in it. And the fourth one, there's something completely wrong. Okay? So a graph of a function should be a set of ordered pairs. So this last one's not even a set of ordered pairs, so that rules that one out. These are not ordered pairs, so that's hopeless. S1 and S3 are okay. The domain of S1 is 0, 3, 1, and 2, and as long as I specify some values for those, that's okay. Doesn't matter there's a repeated value. We know that functions can sometimes have repeated values. What you really have to avoid is repeating the first coordinate unless you give it the same value as well. Now, this second one has a problem because it looks like, say this was the function y equals f of x, whatever that is, then what is f of 0? Well, this pair 0, 1 tells you that f of 0 should be 1. But this pair 0, 4 tells you f of 0 should be 4. F of 0 can't be both 1 and 4, so this is not the graph of a function. F of 0 equals 1 and f of 0 equals 4? No. Okay, that's not allowed. Now, if I had put 0, 1 again, it would have been all right. Because finding 0, 1 in your set again doesn't matter, okay? So that's all right. If you do repeat the first coordinate, you have to give it the same value. And that can happen sometimes in definitions of graphs. S1 and S3 are okay because you've just specified your domain here, 1, 2, 3, 4. You just said what value f of 1 is, what value f of 2 is, f of 3, f of 4, and that's okay. That's a function. So that gives you a graph of a function. So what's the formal definition of a function? Not very useful to us, but I'll tell you what our formal definition of a function is. You see, if you know the graph of a function, you can figure out what the rule is. The rule will tell you the graph, and the graph will tell you the rule. And in the formal pure maths approach, which we're hardly ever going to use,
a function is actually made up of three things. You need to know the domain, the set you're coming from. You need to say what your codomain is, so you can figure out where the values are supposed to be taken, but also various other things about the function, which we're going to do later. And you need to know the graph of the function. And now this is just something about sets, and that's a perfectly formal definition involving sets. And that is generally the pure mathematician, or one of the pure mathematicians' formal definition of what a function is. But we won't usually use that. But bear in mind, though, we will say that if functions are the same, it means they've got the same domain, same codomain, same graph, which tells you it's the same rule as well. Though you say the same rule can be given in more than one way in disguise, so the graph is what wins. And we'll stop there for today.